Greetings. In this video, we are going to see an important problem in the unit linear system with random inputs. Actually, it's a property or problem. It states if x of t is a White's stationary process and if y of t is equal to integral minus infinity to infinity x of t minus u h of u du, then prove that Syy is equal to Sxx omega h of omega modulus h of omega the whole square. So let us understand the terminologies first. X of t here is the input and y of t is the output. H of u is the operator. So the output is defined through the operator. How it is defined? The output is defined as integral minus infinity to infinity x of t minus u, where x is the input signal, okay, into h of u d. In this case, you have been asked to prove that Syy is equal to Sxx into modulus of h of omega the whole square. Here Syy denotes power spectral density of the output, Sxx denotes power spectral density of the input, and h of omega is nothing but Fourier transform of h of tau. What is h of tau? The operator used here. Okay. So, to prove this, actually we'll prove this in 3 steps. So let us see the proof. Before we get into the proof, we should be clear with a few concepts. I'll tell you the concepts to be clear with. The first concept is the concept of convolution. Okay, so the convolution of the two function x of t and h of t is denoted as x of t convolution h of t. How it is defined? It's defined as integral minus infinity to infinity x of t minus u h of u d. Okay, in this case, from this definition, can you say what is integral minus infinity to infinity x of t minus u into h of minus u du will be? Okay, if you get the integral, inside the integral, the product of the form x of t minus u into h of minus u du. How it is defined from the above convolution definition? It is nothing but x of t convolution. In the place of u, we have minus u here. So, in the place of h of t, we should replace h of minus t. This is how we should apply convolution for the function x of t minus u into h of minus u d. We should be clear with this definition of convolution. Second concept is Fourier transform of h of tau is nothing but h of omega. Then what is Fourier transform of h of minus tau will be? Okay, this is how Fourier transform of h of tau is defined. Then what is Fourier transform of h of minus tau? It is nothing but Fourier transform of h of tau conjugate. Okay, so what is Fourier transform of h of tau? It is h of omega. So you will have conjugate on that. So Fourier transform of h of minus tau is nothing but h of omega the conjugate. And the third concept is z into z bar is equal to modulus z the whole square. So these are all the basic concepts we should be clear with to do this proof. And another concepts which we know is power spectral density is nothing but Fourier transform of the autocorrelation, at least correlation. If you want cross power spectral, it is Fourier transform of cross correlation. If you want auto power spectral, then it is Fourier transform of autocorrelation. Accordingly, we will do. What is the formula of correlation? If you want Rxx of tau, the formula is E of x of t plus tau. This is formula of correlation. If we want Rxy of tau, it is expectation of x of t, y of t plus tau. Accordingly, we will do. So, inside expectation, whenever we see product of two functions, it is correlation. What are the function that determines whether it is autocorrelation or cross correlation? What is inside the bracket is nothing but the term here subtract from the previous term. So, t minus t is 0, tau minus nothing is there, so it is tau. So this is how we'll get the correlation function. So if you are clear with all these concepts, we'll move ahead to prove what is being asked. So what is being asked will be proved in 3 steps. The first step, so actually what we have to prove? We have to prove that yes, y of omega is equal to yes, x of omega into modulus h of omega the whole square. This is what we have to prove. So on the left hand side, we have syy of omega. So to get that, first we'll start, we should get what is ryy of omega, because we know syy is nothing but Fourier transform of ryy. So first we'll start with ryy of tau. By definition, what is it? What is it? Expectation of y of t plus tau. What is y of t? Y of t is defined as integral minus infinity to infinity x of t minus u h of u du. Then this is y of t. How it is defined, I have written. Apart from that, what we have? Y of t plus tau. So which is equal to expectation is applied on the function time. So in integral minus infinity to infinity, expectation of only on time function, we apply the expectation. So x of t minus u, y of t plus u. Okay, expectation is applied on that. Apart from that, we have h of u d. Okay, so then how can you write this? Inside expectation, we have product of two functions, means it is correlation R. Some integral minus infinity to infinity R. What are the functions? X, Y. And what is there inside the bracket? So t plus u minus of t minus u. So plus t minus t will get cancelled. And this is tau of y of t plus tau. Okay. Okay. So plus t minus t will get cancelled. So it is tau minus of minus plus u. So r xy of tau plus u h of u d. Okay, now for to express, this is similar to convolution definition, but exactly not. The convolution definition, we should have minus here. So to get exact form, we just go for substitution. Put u is equal to minus t. Or we use some other notation, alpha, because t denotes time, no? So I'll use u is equal to minus alpha. Then du will become minus d alpha. And when u is minus infinity, alpha will become plus infinity. When u is infinity, alpha will become minus infinity. So the integral becomes infinity to minus infinity. R xy of tau, u is minus alpha, h of minus alpha, du is minus d. And we know the property of integration, minus of integral infinity to minus infinity becomes minus infinity. The order changes. Okay. So it differs with sign. So I combine this minus sign with this integral. So it becomes integral minus infinity to infinity r xy of tau minus alpha h of minus alpha d alpha. By note 1, which we have seen earlier, this is convolution. What exactly is convolution? Of the function, first r xy of tau, convolution. What is that? H of, because we have minus there, it is h of minus tau. It's very good. So r xy of tau, h of minus tau, it's a convolution. Now on the left hand side, we started with what? R y of tau. Now we take Fourier transform on both sides. Then Fourier transform of ryy is nothing but syy. So ryy of tau, Fourier transform becomes syy of omega. The right hand side, Fourier transform of rxy becomes sxy of omega. We know Fourier transform of convolution is nothing but product of the transforms. So this is property of convolution of Fourier transform. We use that property. Fourier transform of convolution of two function is nothing but product of its transform. Okay. What is Fourier transform of h of minus tau? Already we have seen, no? The note number, if I'm right, it's 2. The beginning itself we have seen. Fourier transform of h of minus tau is nothing but, yes, h of omega. So mark it as 1. This is step 1. What is step 2? Here actually we have to prove Syy is equal to Sxx into. But instead we have got Sxy. So this term to be changed. For that we are going to repeat the step, similar step. So step 2 is nothing but finding, similar, it will be similar to your step 1. Step 2 is nothing but finding xy, which is there in the right hand side. Okay, we want to find xy. For that we start with rxy. Okay, rxy of tau. By definition, what is rxy of tau? E of x of t, y of t plus tau. But only output function is defined. Y of t is defined as integral minus infinity to infinity. So that definition can be applied only on the output function. So I keep this x of t as such. Y of t can be written as integral. So it is integral minus infinity to infinity h of u x of t plus tau minus u d. Okay. So now I'm going to rewrite it in terms of R again. So which is equal to applying expectation on time function. It is integral minus infinity to infinity e of x of t plus tau minus u h of u t. So integral minus infinity to infinity, inside expectation, product of two functions means it's r. The functions are x, x. So what is there in the bracket? This t plus tau minus u minus t. So plus t minus t will get cancelled. So it is simply tau minus u h of u du. So this resembles the convolution formula. So by the definition of convolution, what is this? Integral minus infinity to infinity rxx of tau minus u h of u du is nothing but convolution of rxx of tau and h of tau. Very good. So in the left we started with what? Rxy of tau. Taking Fourier transform on both sides. Taking Fourier transform on both sides. Rxy of tau becomes, Fourier transform of r is nothing but s. So it becomes sxy of omega, which is equal to Fourier transform of convolution of two functions, nothing but product of its transforms. So transform of rxx is sxx of omega into Fourier transform of h of tau is nothing but h of omega. Mark it as equation number 2. Now we just compare equation number 1 and equation number 2. What is equation number 1? Syy of omega, which is equal to, so we combine both equations 1 and 2. Okay, we'll use 2 and 1. Use equation number 2 in equation number 1. What is equation number 1? Syy of omega, which is equal to sxy of omega. From 2, what is sxy of omega? It is sxx of omega into h of omega. Okay, in the place of sxy, I have used equation number 2. But apart from that, what we have in 1? H of omega bar. But in note 3, we have seen z bar is equal to modulus of z whole square. So how can we write it? Sxx of omega into h of omega bar will become modulus of h of omega the whole square. So we started with syy of omega. We got it as sxx of omega into h of omega the whole square. That is power spectral of output is equal to product of power spectral of input into h of modulus of h of omega the whole square. H of omega is nothing but Fourier transform of the operator h of tau. So once again I repeat, how to prove this we'll be proving it in two steps. One is we'll start with RYY, and hence we'll find by taking Fourier transform we'll find SYY. And in the SYY right hand side we'll be getting SXY instead of SXX. So again we'll be finding SXY. To find SXY, first we'll start with again RXY. Taking Fourier transform, we'll get SXY. So in this way, in two steps, we can easily prove that this is very important result. I hope you have understood this. Thank you.